In this video, I want to introduce the idea of bounding a function. So this will seem to be kind of a very vague thing or maybe mathematical thing, but later on you'll see that this is actually going to be useful to us. So consider the following. Let's maybe look at the graph on the right hand side. So the graph on the right hand side actually has three functions. And let me maybe highlight one of them. So let's say this middle one is called f of n. The idea of bounding a function is to say, okay, I could come up with another function that maybe is always going to be larger than the original function. So let's pretend that's an a there, and this is an n. This function here, right, this left-hand side one, you can see it's shooting up. If we project forward in our mind, that function is probably going to grow pretty fast. It's always going to be larger than f of n. That is what we call an upper bound, right? It's a function, right, that somehow, at the end of the day, it's telling us a little bit about f of n, right? F of n always lives below a of n for sufficiently large values of n. Part of the idea of boundedness is to say, okay, hey, we're going to look at things in the limit, right? This is an asymptotic approach where we basically say that we don't care about, the little behavior here, right? Kind of at the beginning of time. This doesn't matter all that much. Really what we care about is how things behave, right, when n gets really large, right? Generally I use the phrase in the limit, right, because some of the things we'll be looking at, right, basically we'll be saying, okay, I need to take the limit on this function and figure out how it behaves, very long term. So that's what we'll be doing. Again, right, the idea of bounding a function is basically to create a new function which has some relationship to the one we're initially analyzing, right? So a is an upper bound on f of n. We could also have, for example, b of n. b of n appears to be what's called a lower bound, right? So it's something that's lower than, pretend that's an n there that I just wrote, that's always lower than the other function that I'm looking at. And again, this tells me a little bit about f, right? So if I have a and b, I know a little bit about f even if I don't have f directly, and that'll be useful later on. For now, just think about the idea that I have functions basically that can sit on either side of another function to kind of close in on it, right? They kind of give me this kind of limit or this kind of region, right, where I know that f of n is going to be between these two values, perhaps. So that's the idea of boundedness, right? I'm putting a bound that says the function can only go this far in either the upward or the downward direction. So actually, let me answer that little question at the end of the slide. What makes asymptotics useful? Right? What is the point, right, of examining things at the limit? The idea is if I'm using this technique or this idea, right, in terms of growth functions are written for programs. Sometimes when the inputs to programs are really small, strange things happen, right? There's kind of special cases maybe that occur. We're going to avoid that and basically say, okay, for particularly large inputs or particularly large data sets, what happens, right? So asymptotics avoids, right, how we deal with all those little special cases there, right? That little region that I've denoted. And here, let me just cross this out, right? You want to just skip all of that stuff. All right, so that's the basic idea of bounding a function. We're going to explore this idea of an upper and a lower bound. So up until now, we've been using t of n, right? That was the result of the function we got from our empirical analysis. The units on that was basically just time, right? Problem size in, time out. Here what we're going to do is we're going to assume that we have an actual proper growth function, right? And a growth function is going to take in the problem size n, but then its result is going to be the number of operations, right? The number of steps that need to occur in order to solve a problem of that particular size. So for now, what we're going to do is we're actually going to assume that our growth function f of n exists. Later on, we'll talk about how exactly to derive it. For now, we'll just assume that it exists.